Hi everyone, we're so glad that you've joined us at the Center for Brain Health for our event. Let's get started with a brief video underscoring the importance of brain health for you and for society. After that, we'll introduce our speaker.
We work, we live, we innovate and create. At the center of it all is your brain health. The ability to solve problems, think analytically, share empathy, and thrive.
We're trying to make brain performance really the next fitness revolution.
So how do you boost brain power? Welcome to the Brain Health Project, an urgent call to transform your mind to work stronger and faster.
This is an absolute crisis, as great as any we have ever faced. We have to equip the minds and brains of our citizens to cope with the accelerating, dizzying rate of change that they face in their lives.
Your brain health is not fixed. Scientific discoveries prove it can adapt and grow regardless of your starting point.
Our greatest value, the asset that will help us to change everything, every problem we're in, is all in our head.
To harness that treasure, we must measure and monitor progress while things are going well versus waiting for an injury or disease to strike.
Too many of us are outliving our brains, and that does not have to be the case.
The information age is bombarding us with more content than our human brains can handle. How do you keep from getting lost in this? And focus on deep thinking. For starters, stop multitasking.
Science shows us that multitasking is bad for your brain. It reduces fluid intelligence, causes brain atrophy, and increases chronic stress.
The global pandemic is creating more stress than ever, stress that leads to depression and anxiety and beyond. Unlocking our potential to navigate these hurdles starts with learning the right strategies, even in school.
So when teachers have these strategies, they're empowered to support our learners, and then the learners are now able to take ownership of their learning.
Training kids how to think is doubling academic achievement among middle schoolers.
I think the greatest national security threat is pre-K through 12. If we don't take care of educating our young men and women, then we have to ask ourselves, where are we going to be in 20 years?
Our world-renowned scientists know you can increase your brain health, not lose it. It's time for a new category of health, brain health. You are a game changer. Ready to transform the world with us? Be a part of the brain health revolution. It starts here.
Good afternoon, everyone. On behalf of everyone at the Center for Brain Health, I just want to welcome you all to Frontiers of Brain Health, where we take a deep dive into the most exciting new developments in brain research. For anyone who doesn't know me, my name is Dr. Monroe Turner. I'm a computational neuroscientist, and I work closely with Dr. Jeff Spence and others on the neuroimaging part, so where we actually get MRIs of the brain. For the Brain Health Project, which I will be talking about again in just a second here, and we will actually be mentioning more detail at the end of today's presentation. We are, speaking at the end of today's presentation, we are going to have a few minutes at the end, a brief time that everyone can ask questions. So for anyone here, please have questions ready for at the end of the presentation. And if you'll, for anyone watching virtually, if you'll use the Q&A function in Zoom to actually post your question, we'll get to as many of those as we possibly can. For those of us who don't, for those of you who don't know much about us, the Center for Brain Health is a cognitive neuroscience research center here at the University of Texas at Dallas. We've dedicated the past 3 decades to exploring neuroplasticity and the brain's amazing lifelong potential to get stronger and work better. I would encourage everyone to stay until the end of the presentation to hear about our groundbreaking research study known as the Brain Health Project. And now I'm going to introduce you to today's speaker. So Dr. Chris Simmons is the Director of Cyberinfrastructure Research Support at the University of Texas at Dallas. Dr. Simmons earned his Ph.D. from the University of Texas at Austin, in chemical physics, and has over 20 years of experience in computational science. His research portfolio includes leading the collaborative Texas Research and Education Cyberinfrastructure Services, TRECIS Center, and managing a $20 million Grand Challenge PSAAP 1 Center, funded by the DOE National Nuclear Security Administration. He has led several other large CI initiatives and managed activities for an exascale co-design center in turbulent combustion and a DARPA-funded research center in uncertainty quantification. Chris is a developer and a maintainer of several open source projects, including OpenHPC, where he also serves on the technical steering committee and as the cloud lead. And without further ado, Dr. Chris Simmons.
Thank you very much. So today, this might be a little bit of a different talk than you normally see here. I'm going to talk about my career and my history and sort of how I got to this point. And whenever faculty or staff interact with me, they mention things like, I didn't know you did that, or you did that also. And it seems like my portfolio or what I do is a little weird. And when people ask me what I do, I just say, OIT lets me do what I want to do, and they leave me alone. And that's kind of true, but there is a sort of method to my madness. And today, over the next 41 minutes, I'm going to be able to sort of frame my background, where I come from, what I do, and more importantly, what we can do together moving forward. So first, I just quickly want to introduce, I got to turn it on. I work at IT and I can't. Let's see, I turned it on.
Oh, no, it's off.
Oh, no.
Oh.
Okay, it's not my fault then.
If you want to cue me, I can progress your slide.
Ding. Okay, so it's not my problem. Okay, all right, there we go. Okay, so I joined UT Dallas in 2018, about 4 years ago now, and I joined as the third member of the Cyberinfrastructure team. Now, we do sit within the Office of Information Technology. Our boss is G. Vanya. He's the Senior Director of Research Services. And with OIT, we have two cyber infrastructure groups. We have the group of Dr. Jerry Perez, who you might recommend some of his team might recognize some of his team members. They're the research operations group. They do the racking and the stacking and the installation and the feeding and care of the servers, right? And then there's my group, which is researcher support, or the science group. And my group has grown quite a bit. And through a couple of initiatives, we've been able to hire full-time research facilitators who I'm training to be computational rock stars who are available to help you when you need assistance. Next slide. So what I want to do now is sort of tell you a story about sort of the first 15 years of my career, how it caused me to sort of appear at a crossroads, try to dig my way out of a financial hole by funding a very large research group with soft money, and then how I ended up with how I ended up at UTD, and sort of what I've been working on the last couple of years. So as Monroe mentioned, my PhD is from UT Austin in chemical physics. I started my PhD at 97 in Austin, and I was sort of the first generation of graduate student who got an NSF-funded fellowship to be able to use supercomputers for their PhD. Right, the concept of supercomputers were sort of developed in the mid-late 90s at NASA and the Department of Energy. But in the late 90s and the early 2000s, the National Science Foundation was getting in the HPC game. And so being at UT Austin, I was very close to the Texas Advanced Computational Center. And I'll talk about TAC a couple of times in today's lecture. So TAC is one of 4 NSF-funded national HPC centers. There's San Diego Supercomputing Center. There's Illinois Urbana-Champaign. There's the National Center for Supercomputing Applications. There's the Pittsburgh Supercomputing Center at Carnegie Mellon. And there's the Texas Advanced Computational Center at UT Austin. Now, TAC back then wasn't a big NSF center, but they were providing research computing facilities for UT Austin. And during my PhD, I actually realized that the supercomputers didn't map well to my workloads. So I actually had to get some money to build my own cluster. And for those of you who are hardware geeks, in early 2000, basically my memory workloads were too large. I was working on methods that scale as the order of the system to the power of 12. That is, if you double the size of the system, it's 256 times more computationally complex. And so I had these huge, large memory out-of-core workloads, right? They wouldn't fit in RAM. So I had to build a supercomputer that each node basically put 8 hard drives together in RAID 0 in order to create enough storage locally to run my workloads. Now, eventually I finished my PhD. And when I finished my PhD, I was much more interested in how I solved the problem than what problem I solved. My advisor, Dr. John Stanton, he always told me, Chris, you're not a chemist. I was like, I know. He's like, you're a computer scientist. And I'd say, not really, because what I was doing really wasn't computer science, but the concept of computational science, those things that sit at the intersection between science, IT, algorithm, software, really hadn't been formalized yet. So I didn't know what I wanted to do. All I knew is I didn't want to be a faculty member. I didn't want to publish or perish and work on one thing because there were so many cool computers and things out there to work with. So what I ended up doing is joining what's referred to now as the Odin Institute. The Odin Institute is an interdisciplinary research computing center at UT Austin. You can think of it as sort of the research branch of TAC. In fact, TAC was built to serve the Odin Institute. Now, when I joined the Odin Institute, it wasn't called the Odin Institute. It was called ISIS, but obviously due to a namespace collision, they changed the name. But it's the #1 program in the world, still to this day, in computational science. They have graduate programs in computational science, engineering, and mathematics. And graduate students at the Odin Institute have to write 3 PhDs in one. They have to have something about applied mathematics where they do something new. They have to do something new in software and high-performance computing, and they have to do something new in science. So I sort of grew up in this interdisciplinary area, and I was a computational gun for hire. Basically, I knew how to compute, and I jumped from project to project. I've worked in almost every domain of computational science, except neuroimaging. But beyond that, I've worked in turbulent combustion, exascale computing. I've worked in astronomy. I've worked in astrophysics. I've worked in earthquake prediction. I've worked in genomics. I've worked in all manners of chemistry, physics, biology, mathematics, and just kind of drifted around doing really cool things with computers and helping people improve their workflows. Now, in 2008, within the Odin Institute, the PECOS Center was established, which is the Center for Predictive Engineering and Computational Science. And it was started with a $20 million DOE PSAAP Center. That's Predictive Science Academic Alliance Partnership. Basically, it's doing VVUQ, verification, validation, uncertainty quantification, on large-scale simulation. Basically, we were working with NASA and the DOE and using large-scale computational science to design vehicles for atmospheric reentry, ablating vehicles. Why would the DOE care about NASA vehicles? Well, the DOE and NASA have very similar physics. It's just NASA wants to survive when they land. The DOE wants to survive about a second before they land and then deploy a payload. So it was the first time where we're actually doing calculations where it was impacting the design of multi-billion-dollar projects. And in fact, we did some design of optimal thermocouple placement for these ablating vehicles for NASA, where they actually flew the experiment, and it was a multi-billion-dollar effort. And so when you're working on something, you better make sure there's no bugs in your code, right? We're literally running simulations that consumed 400 million compute hours in the late 2000s. Just the simulation was worth around $25 million in power costs, right? And so you really have to do a lot of work to make sure your science, your software, everything is working. And that is an extremely challenging project. And so that gets me through about 2012, which is sort of the first 15 years of my career. Now, when PSAAP 1 ended, we applied for PSAAP 2, and we didn't get it. We didn't get a PSAAP 2 center. And in fact, they told us during our site visit, you guys have too much money. Okay, so we basically, over the last 5 years, built a staff of 20 postdocs and research scientists all on soft money. So we were not able to transition to sustainability, and I'm going to talk more about that a little bit later. So we sort of had to scramble, reduce our staff size, and we had a couple other projects. And over my time at Pecos, we probably had about $50 million worth of funding over those 10 years. And I probably hired 100 postdocs, interviewed over 1,000. And I realized we have several problems with our national education system and how we're training computational scientists. And not only is this a risk for science, but it's also a risk for national security, right? There's not enough trained computational scientists to work at the government labs or the Department of Defense, much less within academia, right? So I realized, and some of my colleagues realized, that there was lots of things we need to do as a community to do things better. So with the rest of the talk, I'm going to talk about the last 10 years. The first 6 years of that, I was still at UT Austin. The last 4 years, I've been at UT Dallas. And the things we learned from the course of running these big programs is we need formal research computing curriculum. We need ways to bring up everyone to equity, right, to an equitable understanding of research computing. We need to address the disparities in campus HPC offerings. In early 2000s and mid 2000s, I was literally only able to interview people at maybe 10 schools, right? Because the other schools just didn't have systems. UT Dallas was a commuter school back then, right? Much less an R1, right? And so I was looking at the same schools, and even with the schools, I was looking mostly in the same groups over and over again, because within a university, there exist disparities, all right? We need better mechanisms to develop the next generation of computational rock stars. Now, when I was hiring for my PSAAP center in 2008, I looked for people who had a background like me. That is, someone who has a science or engineering Ph.D., but they also maintained their group's supercomputers or built servers because they didn't have a campus infrastructure. And those people who knew a little hardware, a little architecture, a little HPC, as well as all the science, were amazingly effective, a factor of 10 to 100 more effective than their colleagues. However, because campus CI and campus HPC centers started to be developed by IT people, that computational rock stars, which were generated organically by supporting their research group's computer, we lost that capability. Now, I don't think when you're working on your PhD, you should have to maintain servers. I think we can capture that pedagogy that occurs without having to maintain an NFS server while you're defending your dissertation, right? And finally, we need better tools for reproducibility of computational science. The tools and methods we developed for our PSAAP center were very tool-centric, right? We were working in finite element analysis, computational fluid dynamics. And so how we went about doing that was very discipline-specific. But I believe and I assert that there's ways to abstract that and approach that problem in a way that is generally applicable by using some of the tools of the public cloud. Right. Next slide. So the remaining of the talk, I'm going to talk about the resulting activities from these 4 lessons learned. The first 2 I'm going to talk about just real quick, and then the last 2 I'm going to talk about in extensive detail, and this is sort of how we can interact. And the last 2 lessons learned is what I've been doing over the last 4 years here at UT Dallas. Next slide. Now, in order to address the disparities in education, we needed some sort of formal curriculum. At UT Austin, I developed a graduate course called Tools and Techniques of Computational Science. It is the core computational course that is required in graduate school for your PhD at the Oden Institute. And this same course has now been sort of proliferated at about a dozen universities for my postdocs over the year. It's taught at Harvard, it's taught at Caltech, it's taught at Berkeley, it's taught at South Carolina, Boulder, Mines. Some of it's taught at A&D, I led A&D research, and we sort of shared the material and sort of tried to train up more people. Now, this class I've also brought to UT Dallas. However, Tools and Techniques of Computational Science was too long to fit the course entry. UT Dallas's course entry has a restricted number of characters, so I renamed it Practical Research Computing. And in my class, I teach sort of the missing skills. Right, we talk about architecture and hardware and Unix and shell scripting compilers, libraries, profiling, debugging, optimization, managing Python and running on HPC systems. Basically all those things that you had to learn for yourself, right? Right now, the typical computational science PhD is this. You spend the first 2 or 3 years passing qualifiers and taking tests, right? Passing qualifiers and taking classes. And then you have about 2 years figuring out what the hell you're doing. And then you try to throw together a dissertation in year 5, right? What I'm trying to do is bootstrap you so when you start working on the actual programming, you're not random walking. Most people develop software based on what they know how to do, not what they should do, right? And you're often limited by your implementation. So I'm trying to teach you sort of a high level how you go about solving those problems. And this course will be offered again next year. It was offered out of the physics department as well as biophysics last year. I'm happy to cross-list it in multiple locations. Just let me know, and I would love to get some of your students or have faculty take my class. Over the last decade, I've had over 100 faculty take my classes, including doing homework and projects. Because when you're a new faculty member and you're trying to build up a research group and no one in your research knows computation, someone has to lead the effort, right? So please take the class. Next slide. The second activity that came out of this was the OpenHPC project. Now, OpenHPC is the largest open source ecosystem for building supercomputers. We have about 40,000 downloads a month. It's used by the majority of R1s, many R2s, smaller schools, and internationally. As Monroe mentioned, I'm a developer and a maintainer. I also lead the cloud effort of OpenHPC. And a couple of weeks ago, I took over as interim project lead as well. This is a 100% volunteer effort. There's about seven of us who support a community of several 100,000. And it's all on volunteer time. So if anyone wants to join, please let me know. We could use some help. Next slide. All right. So for the remainder of the talk, I want to talk about what I've been doing for the last 4 years. Now, as I said, one of the lessons learned is we need a better mechanism to develop the next generation of computational rock stars. Remember, just a second ago, I mentioned how the first generation of computational rock stars were the people who worked on their science PhD, but also supported hardware on their lab, right? But as that moved to centralized campus CI, that educational opportunity was lost. So I've been working on a method to capture that same spirit, but in a much more productive way. Next slide. So the problem is this. Computational science education is rarely formalized, right? My class is one example, but there's very few programs nationally and internationally which are dedicated to computational science. Mostly you learn computational science as an apprenticeship, right? You learn by your lab mates, your peers, your PI, and you just sort of do what everyone else is doing. Most groups often have that one person who understands the software stack, who's been there the longest, who is the fountain of wisdom, right? And that person becomes extremely valuable at the expense of their own time working on their PhD. But I would attest they often get a better education. But that's a discussion for a different day. I was that person for undergrad as well as grad school. Next slide. And when I came to UT Dallas, I was new to research computing support, right? I was a research scientist with my own group, doing my own science. Now, I built supercomputers. We had them in our labs at UT Austin because we developed on HPC systems. But I never did formal research computing support. So my goal when I joined UTD was to find that one person in as many groups as possible. So I've just sort of been working bottom up, right? A lot of you guys probably don't know who I am or found out about me recently. That's because I haven't been advertising, right? I've just kind of been trying to grow organically and get my feet under me. So for groups that had that one person, I worked directly with that person and taught their group, right? Or work with that person who taught their group on my behalf. If a group didn't have that person, I joined their group. I attended group meetings, I helped with software, workflows, education, and tried to bring up that group collaboratively. Now, this one-to-many obviously scales very poorly. Next slide. And what we're missing is the glue, right? The concept is something we refer to as a research facilitator. In the NSF, they have an awful acronym, of course they do, right? They refer to them as ACI refs, Advanced Cyber Infrastructure Research Education Facilitators, right? But these people are the brain drain we've lost. These are the computational rock stars that we really have no formal ways of creating. And the way I think about it is it's the classic infrastructure problem, right? If you want to run a tap, they have resources for you to run there, but they're not going to hold your hand. They're not going to install software. They're not going to, help you run your workflows. They expect that you know how to use the system. So tax the airport, but our users are stuck at the bus stop, and some of our users are still asleep in bed, right? And these facilitators are the Jacks and Jills of all trades. They know a little bit of software, algorithms, IT, HPC, and software domain expertise. And historically, we had a method to generate these organically, but that's been removed as CI and computational science advances. So these users these facilitators help users go from point A to point B and eventually can support themselves and move to TAC or other big national systems. So I like this quote. I don't know who it's attributed to. Maybe I made it up. I'm sure a bunch of people have said it as well. But innovation happens at intersections, right? We like to think of our domain as a one-dimensional or a flat plane, right? And we make little advances there to get our Ph.D., but if you zoom out, you realize your problem is actually multi-dimensional, right? There's many facets. And those people who can collaborate and talk at the intersection of multiple dimensions are extremely valuable, but historically undervalued, especially in our academic system, right? Research staff or support staff don't get the same glory or the same respect as a faculty member, right? So not only are they extremely valuable and rare, we don't treat them well in academia either. Okay, next slide. So the National Science Foundation does fund this work, this workforce development work, but historically the National Science Foundation has focused on taking IT people in central IT who maintain mail servers, Unix servers, et cetera, and teach them a little high performance computing, a little bit of software, and just enough to build a system. And these programs have been extremely successful at getting HPC systems into the hands of the masses, right? Every R1 has an HPC system, most R2s. Actually, I think it's the Open HPC project, which actually did more than the NSF, but maybe I'm biased. Anyway, these same IT pros who know how to build the system don't know how to use the system. They're not scientists. They don't have a workflow. They don't have data, right? The people who are building the systems are not the same people who are using the systems. My approach is different, and it's a funded CC Star Campus Cyberinfrastructure Cyber Team. Next slide. So the first thing I think every IT or CI organization should do is really adopt DevOps. So what is DevOps? DevOps is treating the management of a system as a software development project. Now, Jerry's group, right, is research operations. Operations are logging into a system, fixing it, changing the software, installing MATLAB, deleting MATLAB because MATLAB sucks and we hope no users ever use it again, and then reinstalling MATLAB, right? That's what operations does. Doing things manually does not scale well, and it's not fun. And there's lots of tools out there these days that allow you to manage the deployment of software, hardware, operating systems, just like you manage software. And these tools were developed by Google, Facebook, and Amazon, right? They literally, instead of building 10 servers, they build 100,000 servers. And they're not doing these things manually, right? They're doing them as software development projects. So in general, DevOps, you use some form of version control, which means you use Git these days. You might use GitHub. I personally don't use GitHub for my research because I don't trust Microsoft, right? They bought out GitHub many years ago, but OpenHPC does use GitHub. We have GitLab services here, which is sort of an open source version of GitHub, which I think is objectively better. Other things you do is you use declarative over procedural tools. That is, procedural tools are things where you tell your system to turn this knob, install this package, change that file. And that sort of depends, the output always depends upon the input, right? That is something that's procedural, depends upon the state of the system when you run it. Whereas something that's declarative, you describe what you want the system to look like, and then there's tools to make the system match that state. And declarative tools are a little more abstract, but they're much more powerful. And there's several of them that we can use to actually do research. And finally, the last thing you do with DevOps is you test constantly and automate everything. The second I do something twice, I automate it. My time's too valuable. Okay. Now, on top of that, we try to teach some tools of the public cloud and tools of sort of virtualization. And where we are now is with containerization. And containerization is something that I think is potentially extremely powerful, especially in the neuroimaging space. Now, virtualization you've probably used. This is running VMware or VirtualBox, running Windows on your Mac, right? Running Linux on your Windows machine. And that basically creates a virtual processor and virtual memory, and you run an entire operating system, right? You run a different kernel, et cetera. Containerization is only on Linux. It only runs Linux. And it's virtualization of user space. That is, I'm not running a separate kernel. All I'm doing is having a separate user local, a separate user lib, and putting all those user space packages into a blob that I can then run just like a program wherever I go. Now, Chris, you said containers only work on Linux. I run Docker on my Windows machine. Yes, you do. But underneath the hood, Docker is running a virtual machine of Linux, which is then running the container. So just to let you know. Okay, so my goal is to use only open source tools of the public cloud and automation industry. Aim to use those tools for both IT and science, and keep the IT staff lean, automation, documentation, and then hire these computational rock stars, right? Because that's what we actually need to GSD, get stuff done, right? Next slide. So I took this one person concept and ran with it, talked to a bunch of people on campus, did a multi-campus survey between UT Dallas, UT San Antonio, and UT Arlington, which I also support. As part of this effort, because I don't have enough to do. And we decided to focus on computational chemistry, which of course is my bread and butter, computational biology, and data sciences and machine learning. The reason we focused on these, computational chemistry and machine learning, are of course tools where you do discipline-specific research, but they're also tools who are used by lots of disciplines. They're an enabling technology, right? More than chemists use computational chemistry. Physics, biologists, drug design, right? Materials engineering, mechanical engineering, they all use tools of computational chemistry, and everyone's using machine learning. If you don't know what the hell to do, just throw machine learning at it, right? Machine learning is what you do when you don't know the physics, right? And then computational biology, we have a dire need on campus, right? And as I go through some more of these slides, you might realize that you do have a dire need. Next slide. So the gist of my program is to find graduate students who are about to finish their Ph.D. in the domains of interest who have decided not to go into a faculty career. And normally, these people go to Google, Facebook, financial services, Wall Street, and their first year bonus is more than I make in a year. In fact, over my years, I've had over 10 graduate students hired before they even finish their second year to go directly to Wall Street. Right? And literally their first year bonus is more than I make a year, right? And they don't even finish their PhD. But we have this huge brain drain of these computational, great, students who don't want to go into faculty and don't see a career path. So instead of them going to Google or Facebook and, listening on our phones and trying to sell us something, I bring them on as my postdoc, who then becomes that one person embedded in multiple groups. I train them in research computing support and facilitation. And instead of publish or perish, these postdocs staff a shared ticket pool. They teach formal and informal classes. They teach tutorials at our national computing conferences. PERC is the national NSF computing conference, and supercomputing is our big computational Olympics every year. And in fact, supercomputing's in Dallas this year. We're going to have a really big presence and booth. If you want to come, let me know. I can probably get you a free pass. And it's really fun. My postdocs are required to contribute back to open source projects, software, and or documentation. You can contribute to an open source project without knowing to code. Documentation is always needed. And I contribute to about a dozen open source projects through this mechanism. And I also teach them to write training, workforce development, and hardware proposals. And the goal is to develop these next generation of computational rock stars through a mechanism similar to one that used to exist organically, but we've lost due to the progress of computational science, but to do it in a way that really catalyzes research at its intersections. And then as a secondary goal is to try to change the culture at UT system schools to appreciate and more importantly fund the role of senior staff and research scientists. You know, when I was at UT Austin, I was 100% soft money and every single one of my staff members was 100% soft money. And that's tough, right? You know, we were having $3, $4, $5 million worth of salary every year just to keep the program running. Now, there's a really great program at the Jackson School of Geosciences in UT Austin, and they have research scientist positions that are not tenure track, but they're guaranteed 6 months of funding. So 6 months is soft money that they have to go out and get their own research. 6 months is guaranteed. They tend to give them 12 months of funding for the first 2 years, and they have a backstop mechanism to share them among multiple projects if they don't have their full funding. Now, of course, they have a line item in the state of Texas budget. Thus, they're always going to have that money, right? The state of Texas government only meets 2 years. They don't do anything, right? So that's never going to get removed. But we'd like to set up something similar here and teach us to appreciate this role. All right, next slide. So with this, we're establishing Trekkies. Trekkies is the Texas Research and Education Cyberinfrastructure Services Cloud. We have a new data center provided by UT System. Learn, Lone Star Educational Research Networking helps with the networking. TAC donates old systems as they're retired. They roll off into my center, and then we repurpose them and train systems administrators and facilitators and provide lower barrier of entry services for UT System schools. Next slide. So it's a collaboration between UT Arlington, Dallas, San Antonio, TAC, UT System. Next slide. Later this semester, we'll be launching Europa. It's a 12,000 core high throughput computer. It's going to have web applications for doing all the work you normally do on a supercomputer, terminal access, file transfer, Jupyter, RStudio, full Linux desktops. Trainings are developed by our rock stars and trainings, and postdocs and staff are available for advanced facilitation. Next slide. Europa is in early access. It'll go production later this semester, and you guys, I'll let you know when it's ready for everyone to use. Next slide. We're currently building a portal that you're going to be able to access. You're going to be able to join Trekkies as a student, a mentor, or a researcher. You're going to be able to submit a project to get advanced facilitation. We're going to have a matchmaking service for smaller schools and bigger schools who want to collaborate. There are a lot of opportunities for larger schools to work with smaller schools to get funding. So it's like a tender for PIs. And you're going to be able to submit a ticket or get community support via the Trekkies Project. Next slide. So the last thing I want to talk about is sort of my research, or one of the areas of research I do. And I refer to it as Metaresearch Computing. That is research on how to do research computing, right? Research computing is not a solved problem, right? There's a lot of stuff that can be done to do better. Most of the stuff we do today is just random walk. You come up with a solution, not the best solution, much less even an effective solution. So the way I'm going about this is a science as code approach. That is, I'm treating every aspect of research, including the generation of presentations, publications, papers, whatever, as a software development process. The meta research aspect is using the tools of the public cloud and automation industry to do science. The same thing that runs the millions of servers that Google does, right, to do those reliably and repeatedly, are the same tools we can do to do reproducible science. The benefit is if you guys start using these tools, the overlap of tool usage between IT and scientists increase. And thus it's easier for these systems administrators who don't know science to support you because you're using a more common tool set. And finally, the broader impact is to combat the growing certification over education trend. In the National Science Foundation, they fund HPC systems. Every research computing problem they try to shove into the HPC box because we know how to do HPC and we know how to do it pretty well. Well, 20 years ago, that was all there was. But in the last decade plus, there's this whole Amazon thing. And they've gotten really good at doing some things that we need to do. Because the National Science Foundation is not really funding these cloud-forward efforts as much and funding traditional HPC systems, Google and Facebook are saying, don't go to college. It's a waste of time. They're not training you in what I need you to learn, which are these tools of the public cloud, automation, DevOps type stuff. So instead of getting an undergraduate degree, just go to our 2-year program, right? Our certification over education. And I think it's a very dangerous and horrible trend. And this is one way to combat it. Next slide. So just some concepts of science as code and motivation. So we want to use these tools of DevOps for doing science. We need to version control everything. Most people these days are hopefully version controlling their code. And if you're not, don't just lie to me and then go do it. But I version control everything. Everything in my home directory is version controlled. My data is version controlled. My scripts are version controlled. Everything I do is version controlled. Whenever I move to a new system, all I do is copy my SSH key, check out the Git repo for that project, and then everything is declarative and can be built forward from there, no matter the system I'm on. We've talked about declarative over procedural when possible. I'm also going to tell you the same thing I tell my kids. You're not a beautiful, unique flower, right? You should not be attached to a particular system. If your laptop is the only place you can run stuff, you done messed up, right? If your group is attached to a server or a cluster in their lab, and we have to use it because our scripts are set up to use, I don't know, Sun Grid Engine. But Sun Grid Engine was bought out by Oracle and closed sourced, and no one's using Sun Grid Engine anymore, except about half the people in this room, right? And your things are hard coded for that, and thus you can't move them. So no beautiful, unique flowers. No logging in and installing things manually. Once you do something manually, interactively, you've lost metadata. You're not capturing what you need to recreate it. And I would argue you're not doing science. I would argue that 99+% of papers that involve computation are by definition not science because they're not reproducible. I can't download their code. I don't know what input parameters they used. I don't know what they had to twiddle in order to make the solver converge. I don't know what data they used. I don't know what version of the libraries they used. I just have to take their word that their code works and trust the results. That to me is not science. So I'm trying to fix that. Other concepts, DevDocs. You can treat your documentation as a software development process. Version control, automatically built, everything specified in order to create the document. The final tool we use is what's referred to as CI/CD. It's continuous integration and continuous deployment if it's a server, or continuous delivery if it's a product. And that is everything I need to run a workflow, or build a graph, or generate output, or produce a paper is controlled by checking things into GitHub or GitLab. It automatically spawns an instance, installs your software from declarative or containers, runs the processing, and generates the output. You never store the output. You store the data and the metadata and the processes to generate the output. You never store a plot as a PNG because I guarantee you that ping is going to get divorced from the data and the scripts. And you're going to pull it up and say, this is the data, this is the amazing result I need, and I have no idea where the hell it came from, right? If you've ever done that, you've done messed up, right? You have the opportunities to capture that information and make it reproducible. Now, if we couple all these together, we have something known as literate science in the Knuthian sense. Donald Knuth, scientist. And this is where I'm going, to have all the documentation, the science, and everything together in one package that is always reproducible, location and system agnostic. There's a bunch of famous people who said, of course, Newton's probably most famous for saying it, if I've seen further, it's simply because I've been standing on the shoulder of the giants, right? We do that in science, but in software, we reinvent the wheel poorly over and over again. There's a reason the term academic code base is used as a pejorative, because we don't get paid for software. We get paid for science. Thus, we try to do the minimal software that we can do. All right, next slide. So to give you some examples, within the Trekkies Project, there are 7 projects through 3 universities, which are named projects. One we've been working with Dr. David Lowry, who's also a member of Center for Brain Health. We've done a lot of things with them. We've done a lot of cloud services, elasticity, improving of their code base, increased the performance of their workloads by a factor of 50. Their sensor updates are now happening in real time, literally at the minute scale. They're being updated through a combination of using better protocols for transferring data and more elastic services. And we've worked on a couple of different proposals together. There's a possible collaboration opportunity for people in this room or who are on the call who want to work on the impact of environmental factors on brain health. We're aggregating a lot of this data in real time and building dashboards and environments for people to interactively work with the data. So let me know if you're interested in that. Next slide. We've also been working with Dr. Anna Solodkin in BBS. They have this tool called the Virtual Brain, which is out of Marseille, web-based platform for running neuroscience applications. However, they have to pre-process their data, right? They work with UK Biobank, and there's a lot of pre-processing, FSL, AFNI, a bunch of Python to glue it together. And we've been improving their environment. So we're using containerization and declarative formats for specifying their Python environments. We're using Nextflow to provide automation. Nextflow is a workflow pipeline tool where it's basically a domain-specific language for reproducible science. In a text file, YAML or JSON, you specify the container or the Python environment, where the data is, and how these different steps connect together. Basically, it's a textual representation of a directed acyclic graph, right? And every node of the DAG is an intersection of software, scripts, and data, and it does something. Nextflow abstracts across queuing systems. So you just tell Nextflow you're on a Slurm system, and it submits your workflow to Slurm. You tell it you're on a Sun Grid Engine system. It submits your workflow for Sun Grid Engine. You try to run it, you haven't pulled down the container yet, it pulls down the container for you. You try to run it, your data's not pulled from S3 yet, it pulls down the data for you. You try to run it, your Python environment isn't set up, it sets up your Python environment from a declarative environment in a YAML file, in Git. Everything is captured that you need to reproduce your science. Lastly, we need to finish up here. I'm developing a proposal to take these same concepts we've been applying to Anna's work and apply it to anyone else who's interested at UT Dallas, UT Arlington, or UT San Antonio. We're developing a proposal to implement reproducible neuroimaging pipelines to take your workflows, re-architect them, put them into the system. And then I want to develop a future proposal, possibly an NIH big data proposal, where we integrate this with our storage at UT Dallas and our compute to allow the real-time processing of MRI data. That is, you simply take an MRI here, it writes to your local storage here, and then software we put in place replicates it to our data center. Our data center then inspects that data, tags it with patient name, experiment name, whatever metadata you want, it tags the data set, and then automatically runs this pipeline. You don't have to do anything except take the image and write it to storage. We want to make the science, the software and the processing of the data as painless as possible so we can get it out of your way and do the science. But also, any new person who starts up, literally within 30 minutes of signing on, they should be able to click a button and start running your pipelines, right? That's the goal. The tools to do it are there, but we just don't do it. And that's what I'm trying to fix. Final slide. So basically, what I do is I'm trying to push computational science forward at the intersection of education, cyber infrastructure, workforce development, and research with a focus on equity. And with that, I will take questions. Thank you.
So, Chris, are you arguing we don't have enough of these unicorns, or are you arguing education should produce these unicorns rather than certification? I'm not sure what you're asking.
Okay, so I'm arguing that they don't need to be unicorns. Right now, they are unicorns. And when I joined UT Dallas, they kept saying, we need more Chris's, right? That's what they kept saying over and over again. I was like, please, we don't need more Chris's. My ex-wife would disagree, right? What we need is better training and education and better workflows and just better understanding of what tools are available, right? When working within, research computing in the academic level, we put the blinders on and just use the tools that we've been using forever. And outside of this, the public cloud has caught up and passed us in what they're able to do in terms of reproducible workflows, right? 20 years ago, we were leading the world in computational sophistication.
So I understand the product.
Right.
Are you saying then we need to refocus and create a curriculum to produce these people and have them as our own resource?
Yes, we do. I think we need programs like this. I think we need more interdisciplinary activities, right? We need more people who sit at the intersection of multiple disciplines. And these people exist, and there's methods for training them. I think the sort of this Postop model, embedded model is great for training small numbers of them. Longer term, I do think we need more than just a single or multiple classes. When I finish my IT stuff in a couple of years and I get where I want to be, my next goal is to start a computational science graduate program. Is the next one. And that's what I think we need to do, right? So I think there's a couple of really cool models out there.
But in the meantime, get people in and you can help train them.
And come up with a way to sustainably fund them, right? After 2 years of training them for their postdoc, they are a Swiss Army knife ready to solve any problem, but then we have no mechanism to keep them on as funded staff. It's all soft money, and that's a very stressful life, right? And so even the most noble computational scientist who wants to do good can make 2 or 3 times more by just going to the public cloud and not have to worry about their salary. Yes, sir.
So what is your greatest hurdle with scientists as you leave it? Sounds too good to be true, but we have that. What sort of hurdle and how do you win them over?
So that's a really great question. The most common thing is, this sounds great, but, right? And that but is, it sounds like a lot of work, right? I have to get results out tomorrow, right? And they're always concerned that this type of stuff is going to take more time. And what I have to tell people over and over again is the time you're investing in this will return dividends in the long term, but long is not as far as you think it is. The crossing point or the return on investment is much sooner than you think it is, right? And the other big hurdle we have, especially in this domain, is people who are scared of it. They think it's too hard or they're above it. Some scientists think that's just a trade. Someone else can turn the crank. I'm going to focus on the intellectual merit. But we need to appreciate that there's intellectual merit at every dimension. And your second question?
Aren't you Google?
Because
I mean, it's like, because I can see why Amazon and Google and this kind of expertise. So how are you so noble?
That's a great question. I've been offered 7-figure salaries at Google a couple of times, and I've turned them down every time. I've never had a job that's not in academia. I grew up in Louisiana and Mississippi. I had very poor undergraduate education, a very poor high school education. My high school in Mississippi didn't even teach calculus, right? And I went to University of Southern Mississippi, and my first year, second year there, I met a physical chemist who did his Ph.D. at UT Austin under Ilya Prigogine, Nobel laureate, right, in chaos theory. And he took me under his wing, and every night I would work in the lab, and he would go outside and smoke a cigar, and we would just talk about science. And then I joined UT Austin, and Dr. John Stanton sort of took me under his wing. He only took 2 graduate students at a time. He took a chance on me because he's a rock star, right? One of the most famous electronic structure theory guys in the world. And he taught me. And then in PSAAP, Bob Moser took me on as deputy director. And I was young and unproven. And those 3 people took a chance on me. And they were mentors to me. And I just tried to give back. That's all I've tried to do.
And how did you do that?
Well, my daughter was going to UT Arlington. My son is going to UT Dallas. And I wanted to stay, and I'm divorced. So I wanted to stay until they finished. And UT Dallas has been very supportive. They kind of just let me do what I want to do. And so far, other than, they keep me locked up in a basement. But other than that, I'm pretty much able to do whatever I want to. And what I want to do is just help people do cool stuff. Yes.
So I know that you mentioned, obviously, the problem is these graduate students being attracted away by companies like Google and solutions to get them sort of tied back into the Postdoc program. I wonder if you could also foresee a pathway of attracting people who've been at Google for, say, 10 years and are burned out or are looking for purpose, if you could see a pathway of attracting those people back into research.
That's a great question. And I would love to do it. I have no idea how to do it, right? Once you start living in,
Sandy's super.
Well, there you go, Sandy. That's why I'm here, right? I mean, it's tough. Oh, there is a big burnout rate, right?
So how do we set up a system that funnels it back?
Yeah, that's a good question, and I think some of it has to do with trying to create these long-term positions as staff scientists, right? Like Intel does a really good job of this, right? Intel is able to take away some people from Google and Facebook and academia because they have these senior research scientist positions, which are extremely well paid, and they're basically given a playground to do cool things. I think in academia, we have to play up quality of life, right? But unfortunately, in the IT space, we're always understaffed, right? So it's kind of frantic working in IT as well. So, what we need is institutional support. We probably need some constant source of money, either state budget, right, or endowments, because federal dollars are hit or miss, right? And it's feast or famine. And, constantly for almost every big project I work with at UT Austin, 3-year project, $6 million, first 18 months, bringing everyone on board, ramping up, last 18 months, trying to get something done. And now you have really great staff and they go somewhere else, right? And you just keep teaching the same people the same things over. It's really hard to get this autocatalytic nature, right? This critical mass and become self-sustaining. And that's what I would like to do. I just have no idea how to do it.
Jeremy, what's next?
I am so excited. We could talk. We're going to talk. This is
Of course.
Like, I want to take your class. I want to do everything.
Definitely.
I'm totally on board with all this. So, yeah.
Yes.
All right, so these
Go ahead.
the version control, all these measures for reproducibility are great, and I think it's perfect for if you get a lab set up and they're processing the same type of data over and over again, you can reproduce that because they're doing essentially the same thing with new data. But a lot of science is very novel pathways, new things, new ways to do things. So when you're a grad student or you might even be a PI and you're saying like, well, why don't we try doing this? And nobody's done that before. And so you try all these different versions of libraries, all these different open source projects. How do you get these new projects to be in that reproducible.
Yeah. So there has to be room for experimentation, right? You're going to have to do things interactively at some point, right? You can't just sit down and abstractly design everything and do it, right? The details are dirty, right? But as you're doing it and as you learn something new, right? As soon as you do it interactively, that's the time that you abstract it and then try to automate it, right? So just like you fork code, right? You're familiar with the concept of forking a Git repo, right? There's actually methods to fork models. So if you're doing model development, you can actually fork your code and have a slightly different YAML file and use the concept of forking and branching and merging of science, just like you do for software. All the concepts of software development have a translation to science, and all the tools are there. It's just not immediately obvious. And there are things you can do and tools you can use to version control your data, right? You don't have to store it in Git natively. There are tools to version control your data, like Git LFS, large file support, or other tools. But there's basically a way to version and automate everything. Workflows, pipelines, software, everything can be branched, forked, merged, and versioned.
Innovative. Because it sounds like the question is so good that you're not doing the same thing over and over again. You're like, oh no, I want to ask this now.
Right.
So how do you innovate those kinds of these new queries?
Mm-hmm. Yeah, so you basically fork would be copying. So fork is when you take a current copy of your workflow and copy it to another location and start working on it. And here you make changes. I mean, it's a cheap copy. You have the full version history. You can always go back to the old version, but here you can play. And sometimes forks don't go anywhere. And you can close it or delete it. But once you make a discovery and it worked out, you can then merge that back right into the main pipeline. We have any online questions?
Yeah, I wanted to ask you one from online. I had one as well, and then I think it's going to be about time to wrap up. It's coming up on an hour. One from online. One of the tall hurdles I've experienced repeatedly is management doesn't recognize what they could have, nor do they seem to care. They may give you a reward to feel like they supported the effort, but in reality, they don't understand what could be and are unwilling to support the future use more widely because it would require their effort. Basically, the key DevOps concepts you mentioned are difficult to implement at the company environments I've experienced, although I've tried repeatedly. Any ideas on how to break through? Logic doesn't seem to work.
It's tough, right? Implementing these type of processes from a bottom-up culture perspective are tough, right? If I were just a graduate student in a lab, I would have a hard time convincing someone to do this, right? Or if I'm an engineer at a company, if the company is old school and monolithic and is management heavy, right, and really loves these in-person meetings and these hand-holding, right, it's really hard to implement these things. Now, a lot of the companies that I work with, I have a consulting company, right, and when I work with management and I have a top-down approach where I'm saying, this is what you need to do, trust me, right, and you get the management buy-in, then you have success. But again, at a company level, it's really hard to influence the culture from bottom up. Now, really big, successful, modern companies do this, right? Old school companies that have been around for a long time, certain divisions might, but it's definitely not throughout the entire company. But modern companies that are especially tech forward, they're 100% remote workforce, right? They use these tools daily, and that's how they interact, right? Interacting through these tools and collaborating through these tools guarantee you capture everything to be reproducible, right? And you said you had a question?
Yeah, just as a sort of ending question here, I really found it interesting when you're talking about DevOps and applying it to science. Then you mentioned CI/CD, which got me thinking, do you think there's other aspects of SDLC that can actually maybe be ported over to science? For instance, agile methodology. Maybe not Scrum, more like a Kanban kind of system, but what do you see? Do you see like lessons from those that can sort of be adopted, particularly beneficial, maybe different to others?
Definitely, I think it depends on the scale of the research project, right? If you're working with 1 or 2 students or a small group, I think some of these agile or Kanban methods are probably a barrier to getting things done, right? just simple issues, tickets, right? And maybe a roadmap and documentation is all you need. Now, for these big projects like this PSAAP $20 million center, when I was the deputy director, I was also the project manager, and we ran a Scrum style type of approach. I've had larger projects have Kanban boards, right? And that's one of the reasons we like GitLab, is GitLab has all of this stuff built in. And it's your own data on your own servers. And what's really powerful about running your own GitLab as opposed to GitHub, it's really easy to interface GitLab within your HPC systems, right? And your storage subsystems. And having CI/CD that submit jobs to supercomputers is very powerful. Now, in the beginning of the talk, I mentioned Dr. Georgia Stewart. She's on my team. She recently joined. She's doing some really interesting work. She has a Lagrangian particle tracking code for oil spill cleanups. The source code runs at GitHub. They check changes into the source code at GitHub. It talks to a cloud instance at TAC and then submits jobs to the TAC supercomputers as part of the CI/CD. And that's on the public internet, right? And just works. And that's the kind of thing we want to bring to neuroimaging as well.
Well, I'm just going to go ahead and conclude here. Lifelong brain health. This is our shared mission here at the Center for Brain Health. I want to thank Dr. Christopher Simmons for
in CBH, what's my office number? 3244, something like that. Yeah, by Jeff. And I'll be there with office hours 10 to 2 Tuesdays and Thursdays. Stop by.
We're neighbors.
There we go.
So I got to say, at points, it sounded like you were talking directly to me. I was that guy.
Yeah.
I was the guy.
And I would have hired you.
Exactly.
And he still is the guy.
Thank you. Now just to talk, as I promised, talk a little bit more about the Brain Health Project. The power of research truly lies in how we use it to make the world a better place. So we launched a large-scale landmark study called the Brain Health Project, which will help people everywhere get proactive about maintaining and improving their brain's health and performance. If you are interested in learning more about the Brain Health Project and possibly participating in it, please scan the QR code that you see here on your screen or at home on your actual screen, or you can visit thebrainhealthproject.org, the link that you see right there. Anyone who's interested in continuing education unit credit, you can email ceu@utdallas.edu. I want to one last time thank Dr. Christopher Simmons and everybody who attended today. It was a pleasure hosting you. And I look forward, hopefully, to seeing everyone again on March 4th with Dr. Yoon Lee from UT Dallas will be speaking. See you next time.